Welcome to lecture 20 on measure and integration. In the previous lecture, we had started defining what is called the notion of a function to be an integrable function, and then we started looking at some of the properties of integrable functions. Let us just recall what is a integrable function, and then we will start looking at various properties of these integrable functions, and will prove one important theorem called dominated convergence theorem. So, if you recall, we said a measurable function f on x to extended real valued measurable function f is said to be integrable with respect to mu and written as mu integrable if both the integral of the positive part of the function and the negative part of the function are finite. So, we say f is mu integrable if integral f plus d mu and integral f minus d mu both are finite numbers. And in that case, we say the integral of f is equal to integral of f plus minus integral of f minus. So, let us just once again emphasize saying that a function is mu integrable is if and only if both f plus and f minus are having finite integrals, and the integral of f is written as integral of f plus minus integral of f minus. The class of all integrable functions on the measure space x s mu is normally denoted by L 1 capital L lower 1 x s mu, or sometimes we drop s and mu if they are clear from the context that what are the sigma algebras or what is the measure, or sometimes we just emphasize mu because we want to we know what is x and what is s. So, these are various notations used for denoting integrable functions L 1 x s mu or L 1 bracket x or L 1 bracket mu. So, this is the space of all mu integrable functions. We will start looking at the properties of these functions. The first important thing we observed was a function f is which is measurable is integrable if and only if mod f, which is a non-negative function, is integrable. That means, to check whether a measurable function is integrable or not, it is enough to look at the integral of the function mod f and see whether that is finite or not. And in that case, and this is always true, and for the integrable function, integral of mod f, integral mod of the integral of f d mu is less than or equal to integral of mod f d mu. So, this is an important criteria. This is a equivalent definition, equivalent way of defining integrability of a measurable function, namely mod f is measurable. This is not equal. So, this is wrong here. It should be less than or equal to. So, integral of mod of integral f d mu is less than or equal to. So, this is a typing mistake here. This should have been less than or equal to integral of mod f d mu. Let us recall some of the other properties that we had proved. We said if f and g are measurable functions and mod f is less than or equal to g of x for almost all x with respect to mu, and g is integrable, then f is also integrable. That means, if a function f of x is dominated by an integrable function, then that measurable function automatically becomes integrable. And we also proved the following property, namely, if two functions f and g are equal almost everywhere and one of them is integrable, say f is integrable, then the function g is also integrable and integral of f is equal to integral of g. So, that essentially says that the integral of the function does not change if the function is changed, if the values of the functions are changed almost everywhere. So, f equal to g almost everywhere, f and g measurable functions, and one of them, say f integrable, implies g is integrable and the integral of the two are equal. We also proved the following property, namely, if f is a integrable function and alpha is any real number, then alpha time f is also integrable, and the integral of alpha f is equal to alpha times the integral of f. So, we continue this study of properties of integrable functions, and next we want to check the integrability property, namely, if f and g are integrable functions, then we want to show that f plus g is also integrable and integral of f plus g is equal to integral f plus integral g. So, to prove this property, let us look at what we are given. So, we are given that f and g are integrable functions, that is integral mod f d mu is finite and integral of g d mu is also absolute value of g with respect to mu is also finite. So, to check whether the function f plus g is integrable or not, we have to look at the integral of f plus g absolute value and show that integral of absolute value of f plus g is also finite. But that follows easily, because absolute value of f plus g is always less than or equal to absolute value of f plus absolute value of g. So, and all are non-negative measurable functions. So, using the property of the integral for non-negative measurable functions, this implies that integral of mod f plus g d mu is less than or equal to integral of mod f plus mod g d mu, and that bilinearity is same as integral mod f d mu plus integral mod g d mu, and we are given that both of them are finite. So, this is finite. So, implies that f plus g is integrable. To compute the integral of f plus g, we have to go back to the definition of the integral. So, f and g integrable, so that implies integral of f plus d mu is finite, integral of f minus d mu is finite, integral of g plus the positive part of g is finite, integral of g minus d mu is finite, and we have to show. So, to show integral f plus g plus d mu finite and integral f plus g minus d mu is finite. So, these two properties we have to show. To show this, somehow we have to relate the positive part of f plus g with the positive part of f and positive part of g, and similarly the negative part of f plus g with the negative part of f and negative part of g, and that is done as follows. So, what we do, look at f plus g. By definition, we can write it as f plus g positive part minus f plus g the negative part. So, that is by the definition of the positive part and the negative part of a function. Also, f plus g, we can also write it as decompose f into positive part and the negative part. So, that is f plus minus f minus, and similarly write g as g plus minus g minus. So, now from these two it follows that integral of f not the integral, from this it follows that f plus g positive part minus f plus g the negative part is equal to f plus minus f minus plus g plus minus g minus, right. So, from these two equations it follows this is so. And now, what we do is all the negative terms we shift on the other side of the equation. So, this implies that f plus g plus f minus plus g minus is equal to f plus g plus from here, and this term on the other side will give me plus f plus g minus. So, we just rearrange the terms, and now you observe that the left hand side is a non-negative function and the right hand side is a non-negative function. So, by the properties of integrals for non-negative functions, this implies that integral of f plus g plus d mu plus integral of f minus d mu plus integral of g minus d mu. So, that is the integral of the left hand side is equal to integral of f plus d mu and plus integral g plus d mu plus integral f plus g minus d mu. So, from this equation, by using the properties of integral for non-negative functions, the linearity property, the integral of the left hand side is equal to integral of the right hand side, and integral of the left hand side consists of integral of f plus g plus integral of f minus plus integral of g minus, and that is equal to integral of f plus integral of g plus integral of f plus g minus. And now, we observe that in this equation all the terms are finite quantities, are real numbers. That is because f plus g we have already shown is integrable. So, this first integral of f plus g plus, that is finite, integral f minus is finite, and similarly all the terms are actually non-negative real numbers. So, we can again manipulate them and shift terms on the left hand side and right hand side. So, what we will do is this term f plus g minus on the right hand side will bring it on the left hand side, and the terms f minus d mu integral and integral g minus d mu we shift it on the right hand side. So, that gives us the property. So, shifting implies that integral of f plus g plus d mu minus this term will give you integral f plus g minus d mu. So, this term we have shifted. So, and shift these two terms on the other side is equal to integral f plus d mu, that is this term, and this minus f integral of f minus bringing on this side will give you integral f minus d mu plus integral of g plus d mu, which is already there, and integral of g minus from the left hand side will give you integral of g minus d mu. So, this rearrangement of the terms here once again give you that integral of f plus g plus d mu, and the integral of the negative part of f plus g is equal to integral of f plus minus integral f minus plus integral g plus. And now, by the definition, the left hand side is nothing but integral of f plus g d mu, and the right hand side is integral f d mu plus integral g d mu. So, that proves the linearity property of the integral, that if f and g are integrable functions, not only f plus g is integrable, integral of f plus g is equal to integral of f plus integral of g d mu. So, that is the linearity property of the integral. So, we have proved the basic properties of the integrals, namely the integral of a function which is integrable. Of course, it is a finite quantity and it is linear, namely if you take a function f multiplied by a scalar alpha, then alpha times f is integrable, and the integral of alpha f is equal to alpha times integral of f. And similarly, if f and g are integrable, then f plus g is integrable, and the integral of f plus g is equal to integral of f plus integral of g. Let us look at some more properties of this integral which are going to be useful later on. So, let us look at the next property. So, for an integrable function f, so f in L 1 of mu, let us look at we have already shown that if you mod f is a non-negative measurable function and if you multiply it by the indicator function of a set E, then we have already shown that this is again a non-negative measurable function, and of course, this function is less than or equal to integral of mod f. So, nu of E is going to be always a finite quantity. So, the claim is nu is a measure, in fact a finite measure, and it has the property that mu of E equal to 0 implies nu of E equal to 0. So, whenever a set E has got mu measures 0, the measure of nu also is going to be equal to 0. And this basically follows from the properties of the integral for non-negative functions, because if f is integrable, then mod f is a non-negative measurable function and its integral is a finite quantity. So, nu of E is a finite measure for every E, the function chi E times mod of f is less than or equal to mod f. So, this integral is going to be less than or equal to integral of mod f, which is finite. And obviously, for non-negative functions, we have already proved this property that for if mu of E is 0, then the integral over E is equal to 0. So, this property follows from our earlier discussions. Let us look at the integral of for the integrable function, not the integral of mod f, but let us look at the integral of f times indicator function of E. And if you recall, we had already shown that if f is measurable and E is a set in the sigma algebra, then chi E times f is again a measurable function. And just now we observed that this number is going to be a finite number, because this is again a integrable function. So, let us just observe this property once again, that if f belongs to L 1 of mu and E is a set in the sigma algebra, then this implies that chi E times f is a measurable function. So, that we have already seen, because f is a measurable function, indicator function of E is a measurable function. So, product of measurable function is measurable, and we observed just now, if you look at the absolute value of chi of E times f, that is same as indicator function of E, because that is negative, into absolute value of f. So, this implies that the integral of chi E times f absolute value d mu is less than, actually is equal to integral chi E of mod f d mu, and which is less than or equal to integral mod f d mu, which is finite. So, what does that imply? So, this implies that integral chi E d mu is a, so this we are denoting it by nu tilde of E. So, this is a real number, is a finite real number. So, that is the observation, and we want to claim that mu of E is equal to 0 implies that nu tilde of E is also equal to 0. So, the claim is that this property. So, let us prove this property. So, suppose mu of E is equal to 0, then what is nu tilde of E? Nu tilde of E by definition is integral chi E of f d mu, which is same as the integral of chi E f plus d mu minus integral chi E f minus d mu. And now, we observe mu of E equal to 0, chi E of f plus is a non-negative function, and for properties of non-negative functions imply if the set has got measure 0, then the integral of this is equal to 0. So, the first integral is equal to 0, second integral is equal to 0 by properties of integrals of non-negative measurable functions. So, implies nu tilde of E equal to 0. So, what we are saying is mu of E equal to 0 implies nu tilde of E is also equal to 0. So, that is a property we are proving here. But keep in mind that nu tilde of E is defined as a real number for every E belonging to S, but it is not a non-negative number, because f may not be a non-negative function. So, we cannot say nu tilde of E is a measure. We will look at this property a bit later. It may not be a measure, but it has some property similar to a measure. Here is another important property. Let us look at again the same value nu tilde of E, which is equal to integral of f over E d mu, and suppose this is equal to 0 for every set E in the sigma algebra. Then the claim is, then this function f must be equal to 0 for almost all x belonging to mu. So, let us prove this property, namely, so let us so given nu tilde of E, which is nothing but integral chi E times f d mu is equal to 0 for every E belonging to S. So, that is what is given to us, and we want to show that if we take the set n, which is x belonging to x, such that f of x mod f of x bigger than 0, if I write this set n, then note that this set n is a set in the sigma algebra, and we want to show that mu of n, right. We want to show f is 0 almost everywhere, and this is a set where f is not 0. So, we want to show this is equal to 0. So, this is the problem we want to show. Now, let us look at, consider the set, say for example, let us write the set, say A n to be the set where x belongs to x, say that f of x is bigger than 1 over n. And similarly, let us write B n to be the set of x belonging to x where f of x is less than minus 1 by n. So, now the claim is that the set n is nothing but union over A n, union over B n, n equal to 1 to infinity, union of union n equal to 1 to infinity. That means, all these sets A n's and B n's, if you take their unions, that is precisely the set n where n is n, and what is the set n? N is a set where f of x is not equal to 0. So, if f of x is not equal to 0, then either f of x is positive or f of x is negative. So, if it is positive, then it is going to be bigger than 1 over n for some n. So, if x is positive and bigger than 1 over n, then it is going to belong to 1 over n. Or if f of x is not 0 and it is negative, that means it is negative. So, it is going to be less than 1 over minus 1 over n for some n. So, it belongs to B n. So, every set n, every point x in n either belongs to A n or belongs to B n, and obviously, if x belongs to A n or B n, then f of x is not equal to 0. So, it belongs to n. So, n is equal to this. So, n is written as a countable union of sets, and all of these are sets in the sigma algebra S, and we want to show this union has got measure 0. So, in case mu of n is not 0, that will mean for some n, either A n has got positive measure or B n has got positive measure, because otherwise mu of n will be less than or equal to sigma mu of A n's plus sigma mu of B n's, all of them equal to 0. So, let us write what we are saying is the following: to show that mu of n is equal to 0. So, suppose mu of n is bigger than 0. then that implies, then this condition implies there exists some n naught such that either mu of a n naught is bigger than 0 or mu of b n naught is bigger than 0, because if not, then mu of n will be equal to 0. So, let us look at these conditions. So, suppose the first one holds, if mu of a n naught is bigger than 0, then look at the integral, then integral of f, okay, then integral of f over the set a n naught, let us look at. So, let us look at integral of f over the set a n naught. So, that is equal to integral, so which is same as integral chi a n naught times f d mu. Now, on the set f a n naught, f is bigger than 1 over n. So, this is bigger than obviously integral 1 over n times n naught times mu of a n naught. So, let us observe that on the set a n naught, outside a n naught this function is equal to 0, indicator function of a n naught times f, that is 0, and on a n naught f is bigger than 1 over n naught. So, this function is bigger than 1 over n naught, right, and outside a n naught is 0. So, this is going to be bigger than, so it is bigger than integral over a n naught of 1 over n naught d mu. So, that is what we are saying. So, once that is true, and this is nothing but this integral, and that is bigger than 0. So, in case mu of a n naught is bigger than 0, integral of f over a n naught is going to be bigger than 0, which is a contradiction, because which is not true, because we are given integral of f over every set E is equal to 0, which is not true. So, if this holds, then it is a contradiction. Similarly, if this holds, one can prove it is a contradiction, then the integral of f over b n naught will be less than, strictly less than 0, not equal to 0. So, in either case, both of these are not possible. So, our assumption that mu of n naught is bigger than 0 must be wrong, and hence mu of n. So, implies that the measure of the set n is equal to 0, and n was the set where n was the set where f of x is bigger than 0. So, this set has got measure 0. So, this is what we wanted to prove. So, we have proved the property that if integral of a function over f is an integrable function, and its integral over E is equal to 0 for every E belonging to S, then f must be equal to 0 almost everywhere. Okay. So, this is a very nice property and useful property.